Tonight we're going to talk about something that sounds impossible, and yet may be the deepest truth physics has ever whispered to us. That the moment you call gone is not gone at all. That the past is not behind you, but beside you. And that every breakfast, every goodbye, every ordinary afternoon you've ever lived is still unfolding somewhere in the architecture of reality, as real and as present as the breath you're taking now. Imagine a daughter sitting at the edge of her father's bed in the last days of his life. The room is quiet. The afternoon light comes through the blinds in soft angled bars. His breathing is shallow and slow. She's holding his hand and she's thinking about breakfast. Not the breakfast they will have tomorrow, because there may not be a tomorrow. She's thinking about a breakfast from 20 years ago, when she was small and he was strong, and they sat together at the kitchen table on a Saturday morning in June. There were pancakes and sunlight on the tablecloth, and he was telling her a story about something that happened at work, and she was laughing. She cannot remember the story now. She cannot remember what he said. But she remembers the feeling of it, the shape of that morning, the way the world felt large and safe and unhurried. And what she wants more than anything is to go back. Not to change it, not to fix anything, just to be there again, for 5 minutes, and to know while she is there that it matters, but she cannot go back. The breakfast is gone. It happened once and then it ended, and now it belongs to a place we call the past, which is another way of saying it belongs to nowhere at all. We treat the past as a grave. We say things like, "Those days are over, and it is all behind me now," and we mean that the moments themselves have been erased, that they flickered into existence and then dissolved, and that nothing remains but the memory, which is fragile and fading and kept alive only by the effort of minds that will themselves one day go dark. This is what we are taught to believe about time. The present is real, the past is gone, the future has not happened yet, and we, all of us, are riding a narrow edge called now, and everything that falls off that edge is lost. But in the spring of 1905, a young man working in a patent office in Switzerland looked closely at the way light moves, and at the way clocks tick, and at the question of what it means for two events to happen at the same time, and he concluded something so strange that it overturns the entire picture. He concluded that there is no single moment called now, that observers moving at different speeds will disagree, fundamentally and irreparably, about which events are happening at the same time. That simultaneity is not a feature of the universe, but a feature of your reference frame, and if that is true, if there is no universal present tense, then the past cannot be gone, because gone implies a kind of now that does not exist. The breakfast is still there. The Saturday morning in June is still unfolding. It is just not here, in the sense that here is a place you're pointing to in space. It is there, in the sense that there is a place you're pointing to in spacetime, and spacetime does not forget. By the end of tonight, you're going to understand exactly how Einstein arrived at this conclusion, why the speed of light forces the present to fracture, and why the structure of relativity suggests, with quiet and unyielding logic, that your life is not a candle burning down, but a sculpture that exists all at once, and that only your attention moves through it. We're going to sit with Einstein in the patent office, walk through the thought experiments that crack the old picture open, follow the clocks and the twins and the horizons that proved him right, and then face the question that lies beneath it all. If every moment of your life is still real, still happening, still there in the four-dimensional map, what does that mean for the daughter at the bedside, and for all of us, and for the way we think about loss? Now, let us begin. The city of Bern, Switzerland, in the early years of the 20th century was a place of stone arcades and tram lines and church bells that rang on the quarter hour. The river Aire wound through it in a wide green loop, and the old town sat inside the loop like a ship at anchor, its medieval streets narrow and clean, its buildings fronted in sandstone the colour of honey. It was not a large city, it was not a famous one, but it was orderly and it was prosperous, and in the year 1905 it was home to a young man who was about to dismantle the architecture of time. His name was Albert Einstein. He was 26 years old. He had a wife, Mileva, who had studied physics alongside him in Zurich, and a young son named Hans Albert, who was not yet 2. They lived in a small apartment on Kramgasse, a cobbled street in the heart of the old town, in a building with thick walls and high ceilings and windows that looked out over the rooftops toward the distant peaks of the Bernese Alps. Einstein worked 6 days a week at the Swiss Federal Office for Intellectual Property, a patent office housed in a large building near the main post office, and his job was to examine patent applications for electrical devices, synchronization systems, and various instruments that depended in one way or another on the measurement of time. He was employed as a technical expert, 3rd class. His salary was 292 Swiss francs per month. It was enough to live on, but not much more. He had applied for academic positions and been turned down. He had submitted a doctoral thesis and had it rejected. The patent office was not where he had imagined his life would take him, but it gave him a desk and a window and long stretches of uninterrupted quiet, and in that quiet he thought about light. He had been thinking about light for years, not in the way an optician thinks about it, or a painter, but in the way a physicist thinks about it, as a thing that moves and that has a speed, and whose speed might mean something. The speed of light had been measured. It was known to reasonable precision to be about 300,000 kilometers per second, and the peculiar thing, the thing that no one quite knew what to do with, was that light seemed to move at that speed no matter how you were moving when you measured it. If you were standing still, light passed you at 300,000 kilometers per second. If you were running toward the source of the light, it still passed you at 300,000 kilometers per second. If you were running away from it, same thing. The speed did not add or subtract. It did not care about your motion. It was the same for everyone. This was not how speeds were supposed to work. If you were standing on a platform and a train rolled past you at 60 kilometers per hour, and someone on the train threw a ball forward at 20 kilometers per hour, you would see the ball moving at 80 kilometers per hour, speeds added. That was common sense, and it was also the foundation of the physics that had been taught in every university in Europe for 200 years, the physics of Galileo and Newton, in which time was absolute and space was a fixed stage and motion was just a question of how fast you were moving across that stage. But light did not behave that way. Light somehow moved at the same speed relative to everyone, and no one knew why. Einstein knew that this constancy was built into the equations James Clerk Maxwell had written down in the middle of the previous century. Maxwell had been a Scottish physicist, reserved and religious, who had spent years trying to understand electricity and magnetism, and who had realized, in the 1860s, that the two forces were aspects of a single phenomenon, and that this phenomenon could ripple through space in the form of waves. He had written down 4 equations that described those waves, and buried in the equations was a number, the speed at which the waves propagated. It was the speed of light. Maxwell had not put it there by hand. It had emerged from the structure of the theory, and it did not depend on the motion of the source or the observer. It was simply there, like a fact of geometry. But if the speed of light was truly constant, then something else had to give. You could not have absolute time and absolute space and a universal speed limit all at once. Something in the old framework had to be wrong, and in the summer of 1905, sitting at his desk in the patent office, Einstein realized what it was. It was time itself. Time was not absolute. There was no universal clock ticking away in the background of the universe, no single timeline that everyone agreed on. Time was something that depended on motion, and the thing that tied all of this together, the thing that forced the entire picture to change, was a question Einstein had been circling for months. What does it mean to say that 2 events happen at the same time? Picture this. You are standing on a railway platform. It is evening. The platform is straight and level and empty. A train approaches from the left, moving fast, and as it passes you, 2 things happen. Lightning strikes the front of the train. Lightning strikes the rear of the train. The flashes are bright and sudden, and you see them both at exactly the same moment. From your perspective, standing midway along the platform, equidistant from both strikes, the two events are simultaneous. They happened at the same time. But now consider someone else, a passenger, sitting in the exact centre of the train, midway between the front and rear. The lightning strikes in precisely the same places as before, the front of the train and the rear of the train. But this passenger is moving, and because the passenger is moving forward toward the front of the train, they are moving toward the light coming from the front strike and away from the light coming from the rear strike. Light, remember, travels at a fixed speed. It does not care that the train is moving. So the light from the front strike reaches the passenger first. Then, a moment later, the light from the rear strike arrives. From the passenger's perspective, the two lightning strikes did not happen at the same time. The front strike happened first. The rear strike happened later. And this is not because the passenger made a mistake, or because the light was delayed by some mechanical quirk. It is because, for the passenger, the two events genuinely occurred at different times. The passenger and the observer on the platform are both right. They have simply measured time from different vantage points, and time, it turns out, is not something you measure. It is something you construct, relative to your motion. This was the heart of Einstein's realization. There is no universal now. The present tense is not a single, shared moment that everyone in the universe agrees on. It is a local fact tied to your motion, and two observers moving at different speeds will slice the universe into different presents. Events that are simultaneous for you are not simultaneous for someone moving past you at high speed. And if simultaneity is not absolute, then neither is the distinction between past and future. The ordering of events, the sense that one thing happens and then another, becomes, for events separated by distance, a matter of perspective. Einstein called this the relativity of simultaneity. It was not a paradox. It was not an illusion. It was a structural feature of space-time, as real and as unavoidable as the fact that parallel lines do not meet. And it followed, with the clean and merciless logic of mathematics, from a single assumption, that the speed of light is the same for every observer, no matter how they are moving. He wrote it all down in a paper that spring. The title was sober and technical, On the Electrodynamics of Moving Bodies. It ran to 30 pages. There were no footnotes, no citations except for a brief acknowledgement of his friend Michel Bessot, an engineer at the patent office who had listened patiently while Einstein worked through the ideas aloud. The paper was received by the journal Annalen de Physique on the 30th of June, 1905. It was published in late September. It did not announce itself as a revolution. It simply stated, step by step, what had to be true if the speed of light was constant, and then work through the consequences with a kind of patient, inexorable care. But the revolution was there, in the third section of the paper, in the discussion of simultaneity. Einstein had taken the thing everyone assumed was obvious, the thing no one had ever thought to question, that there is a single, universal present moment, and shown that it could not be true. And if the present is not universal, then the map of reality has to be redrawn. Think for a moment about what this means. We walk through the world assuming that the past is behind us, and the future is ahead of us, and the present is this razor-thin edge we are balanced on, the only moment that is real. We talk about time as though it flows, as though it carries us from one moment to the next, and as though the moments we leave behind vanish as we go. But if there is no universal now, if different observers carve the universe into different present moments, then the idea that only the present is real becomes impossible to sustain. Because whose present are we talking about? Yours? Mine? The present of someone moving past Earth at 90% of the speed of light? Einstein had not set out to overthrow the common-sense picture of time. He had set out to understand how light moved. But in solving that problem, he had opened a door onto something far stranger. The possibility that time is not what we thought it was. That it is not a river carrying us forward, but a dimension, like space, and that the past and future are not gone and not yet arrived, but simply elsewhere, in the same way that a distant city is not non-existent but merely far away. This idea, this quiet and unsettling implication, would take decades to unfold. But it was already there, in the summer of 1905, in a paper written by a young man at a standing desk in a patent office in Bern. A man who had spent years thinking about clocks and trains and the strange, unchanging speed of light. The problem Einstein had inherited was not one he had chosen. It had been handed to him by the previous generation of physicists, men who had spent decades trying to reconcile the laws of motion with the laws of light, and who had found, to their growing frustration, that the two sets of laws did not fit together. The laws of motion, codified by Isaac Newton in the 1680s, said that time was absolute. It flowed uniformly, everywhere, for everyone, like a river that carried the entire universe forward at the same rate. Space was absolute too, a fixed stage on which events unfolded. Motion was relative, your speed depended on what you were measuring it against, but time and space themselves were not. They were the background, unchanging and universal, but the laws of light, written down by James Clerk Maxwell in the 1860s, said something different. Maxwell's equations described how electric and magnetic fields rippled through space, and those ripples moved at a specific speed, the speed of light. The strange thing was that this speed appeared nowhere in the equations as a variable. It was a constant, built into the structure of electromagnetism itself, and constants are not supposed to depend on the motion of the observer. If the speed of light was truly a constant of nature, then it should be the same for everyone, regardless of how fast they were moving. This presented a puzzle. In Newton's framework, speeds added and subtracted depending on your motion. If you were chasing a beam of light, you should measure it moving more slowly relative to you. If you were running away from it, it should appear to move faster. But Maxwell's equations did not allow for that. They insisted that light always moved at the same speed, no matter who was measuring it or how they were moving. One set of laws said speeds were relative. The other set said light speed was absolute. They could not both be right. The response of most physicists in the late 19th century was to assume that light, like sound, must travel through some medium, and that this medium provided a universal reference frame, a kind of absolute rest. They called the medium the luminiferous ether. It was imagined as a substance that filled all of space, invisible and intangible, but capable of transmitting electromagnetic waves the way air transmits sound waves. If the ether existed, then the speed of light would be constant only relative to the ether. If you were moving through the ether, you should be able to detect a change in the speed of light, a kind of wind blowing through the fabric of space. In 1887, two American physicists, Albert Michelson and Edward Morley, built an experiment to detect that wind. They used an interferometer, a device that split a beam of light into two perpendicular paths, bounced them off mirrors, and brought them back together to form an interference pattern. If the Earth was moving through the ether, the light travelling in the direction of the Earth's motion should take slightly longer to return than the light travelling perpendicular to it, and the interference pattern should shift. They mounted the interferometer on a massive sandstone slab floating in a pool of mercury, so it could be rotated smoothly, and they measured the interference pattern at different orientations. They expected to see a shift. They saw nothing. The speed of light was the same in every direction, no matter how the apparatus was oriented, no matter what time of year they performed the experiment. It was a null result, and it was baffling. Either the Earth was not moving through the ether, which seemed absurd, or the ether was somehow being dragged along with the Earth, which raised more questions than it answered, or something deeper was wrong with the picture. A Dutch physicist named Hendrik Lorentz tried to save the ether hypothesis by proposing that objects moving through the ether contracted slightly in the direction of motion, and that time slowed down for moving clocks just enough to make the speed of light appear constant. He derived a set of mathematical transformations that described how lengths and times would need to change between reference frames in order to preserve the constancy of light's speed. The transformations worked. They predicted the null result of the Michelson-Morley experiment. But they were ad hoc, a mathematical patch applied to a theory that was straining under the weight of its own contradictions. Lorentz himself did not fully believe them. He thought of the contraction as a physical effect caused by motion through the ether, not as a feature of space and time themselves. In France, a mathematician named Henri Poincaré pushed further. He argued that the principle of relativity, the idea that the laws of physics should look the same in every inertial reference frame, should apply not just to mechanics but to electromagnetism as well. He wrote about the impossibility of detecting absolute motion and about the need to redefine simultaneity in a way that was consistent with the finite speed of light. He came very close to what Einstein would later publish. But Poincaré, like Lorentz, still thought in terms of the ether. He treated the transformations as mathematical tools, useful for making predictions, but not as descriptions of physical reality. Einstein came at the problem from a different direction. He did not try to save the ether. He did not try to explain why objects contracted or why clocks slowed down. He simply started with two assumptions, both of which he considered unavoidable. The first was the principle of relativity. The laws of physics must be the same in all inertial reference frames. The second was the constancy of the speed of light. Light moves at the same speed for every observer, regardless of their motion. If you took those two principles seriously and followed them to their logical conclusion, everything else fell into place. You did not need the ether. You did not need a universal reference frame. What you needed was a new understanding of space and time. The price of making light speed absolute was that time itself had to become relative. Cloaks in different reference frames could not stay synchronized. Lengths in different reference frames could not agree. And simultaneity, the idea that two events happened at the same time, could no longer be a universal fact. It became a coordinate-dependent statement, true for one observer and false for another. This was not a small adjustment. It was a complete rebuilding of the foundation. Newton had said that time flows uniformly, the same for everyone, everywhere. Einstein said no. Time is not a river. It is a coordinate, like space, and its value depends on your motion. The universe does not have a clock. It has clocks, plural, one for every observer, and they do not all agree. And if they do not agree about time, they cannot agree about which events are happening now, which have already happened, and which are yet to come. The ordering of reality itself becomes observer-dependent, and so the question returns, quieter now, but heavier. If there is no universal now, if the present moment is not something the universe possesses, but something each observer constructs, what does that mean for the past? Is the breakfast still there, in some frame of reference still unfolding in some slice of space-time that is present for an observer moving at the right speed? And if it is, if the moment is still there, still real, still part of the four-dimensional structure of the world, then what has the daughter lost, and what does it mean to lose anything at all? The question hangs there, unanswered, because answering it requires one more piece of understanding. The relativity of simultaneity tells us that different observers disagree about which events are happening now. But it does not tell us whether that disagreement has limits. It does not tell us whether there are some orderings of events that everyone must agree upon, regardless of how fast they are moving or in which direction. And without knowing where the boundaries lie, the whole picture threatens to collapse into a kind of chaos, where causes and effects can swap places depending on who is watching. So let us be precise. Let us imagine two events, separated by a great distance and by some span of time. The first event is a supernova, a massive star collapsing in upon itself and then rebounding in a catastrophic explosion, somewhere in a distant galaxy. The light from that explosion has been travelling for a very long time, and on a particular evening, it finally reaches Earth. An astronomer, sitting at a telescope in a quiet observatory, sees the flash. That is the first event, the arrival of a light from a star that died long ago. The second event is simpler. A spacecraft somewhere in the outer reaches of our own solar system sends a routine signal back to Earth. A small burst of radio waves carrying telemetry data, travelling at the speed of light toward a receiving station. That is the second event, the transmission of a message from a machine far from home. Now, from the perspective of an observer on Earth, these two events might appear to happen in a particular order. Perhaps the supernova light arrives first, and then, some hours later, the spacecraft signal is received, or perhaps the reverse. The specific order depends on the geometry of the situation, on where the spacecraft is, on how far away the supernova is, on the timing of the transmission. But here is the crucial point. If the spacecraft is far enough away, and the supernova is far enough away, and the two events are separated by enough distance relative to the time between them, then there is no way for one event to have caused the other. The supernova did not trigger the spacecraft's transmission. The spacecraft's transmission did not cause the supernova. They are, in a very specific sense, disconnected from one another. No signal, no influence, no chain of cause and effect links them, because no signal could have travelled from one to the other in the time available. When two events are related in this way, when the distance between them is greater than light could have crossed in the time between them, physicists say they are space-like separated. And for space-like separated events, the relativity of simultaneity applies in full force. Different observers, moving at different speeds, will disagree about which event happened first. An observer on Earth might say the supernova light arrived before the spacecraft's signal. An observer on a rocket ship, moving at tremendous speed in a particular direction, might say the spacecraft's signal was sent before the supernova light arrived. And both of them would be correct, within their own reference frames. There is no fact of the matter about which event happened first. The ordering is relative. This is strange. It is deeply strange. But it is not dangerous. It does not lead to paradox because the two events cannot influence one another. It does not matter in any causal sense which one happened first, because neither one could have caused the other. The disagreement about ordering is a disagreement about bookkeeping, about how to assign coordinates to events that have no causal connection. It is not a disagreement about what happened, only about when. But now consider a different pair of events. Imagine that the spacecraft, instead of sending a routine signal, receives a command from Earth. A message is transmitted from a ground station, travels across the solar system at the speed of light, and arrives at the spacecraft. The spacecraft then executes the command, perhaps firing a thruster or adjusting an instrument. Here we have two events, the sending of the command and the execution of the command. And these two events are very different from the supernova and the signal. These two events are causally connected. The sending of the command caused the execution of the command. One event led to the other. There is a chain of influence linking them, a chain that travelled at the speed of light or slower. For events like these, the ordering is not relative. Every observer, no matter how fast they are moving, no matter in which direction, will agree that the command was sent before it was executed. They might disagree about how much time passed between the two events. They might disagree about the distance between them, but they will all agree on the order, because comes before effect. The message was sent before it was received. The decision was made before the action was taken. This ordering is absolute, unchanging, written into the structure of space-time itself. The difference between these two cases is not a matter of convention or definition. It is a geometric fact. In the mathematics of relativity, there is a quantity called the space-time interval, a kind of distance measured not in space alone but in the combined fabric of space and time. For two events that are causally connected, for two events where one could have influenced the other, the interval has a particular character that physicists call time-like. For two events that are causally disconnected, where no influence could have passed between them, the interval has a different character called space-like. And the nature of the interval determines whether the ordering of the events is absolute or relative. This is where the geometry becomes visible. Imagine a point in space-time, a single event, a particular place at a particular moment. From that point, light can travel outward in all directions. As time passes, the light spreads, forming an expanding sphere. But in the four-dimensional picture of space-time, where time is just another coordinate, that expanding sphere traces out a cone. The cone opens toward the future, and it also extends backward toward the past. This is the light cone, and it is the boundary that separates what can be causally connected from what cannot. Everything inside the future light cone of an event is everything that event could possibly influence. A signal sent from that event travelling at the speed of light or slower could reach any point inside the cone. Everything inside the past light cone is everything that could possibly have influenced the event. A signal arriving at that event could only have come from somewhere inside the cone. And everything outside the cone, everything in the regions that physicists call elsewhere, is causally disconnected. No signal could have travelled from the event to those regions, and no signal could have arrived from those regions to the event. They are out of reach, not because of technological limitations, but because of the structure of space-time itself. The light cone is not a metaphor. It is a geometric object, as real and as rigid as the angles of a triangle, and it is the same for every observer. Different observers might disagree about which events are simultaneous. They might disagree about the distances between events or the times between them, but they all agree on the light cone. They all agree on which events are inside it and which are outside. They all agree on which events could have caused which other events. This is how relativity protects itself from paradox. The relativity of simultaneity applies only to events that are space-like, separated, only to events that cannot influence one another. For events that are causally connected, for events where one could have caused the other, the ordering is fixed. No observer can see the effect before the cause. No reference frame can reverse the arrow of causation. The universe allows disagreement about the bookkeeping of disconnected events, but it does not allow disagreement about the chain of cause and effect. And so the strange freedom of relativity, the freedom to disagree about which events are happening now, turns out to be bounded. It is not a license for chaos. It is a carefully structured flexibility, permitted only where it cannot do any harm. The past and the future as categories are not simply matters of perspective. They are defined by the light cone, by the geometry of what can influence what. The past is everything that could have shaped the present. The future is everything the present could shape, and the elsewhere, the vast expanse of events that are neither past nor future, is simply beyond the reach of causation. This is the framework that Einstein's equations implied, though Einstein himself did not immediately see it in geometric terms. That insight would come from someone else, someone who had once been Einstein's teacher, and who would transform the mathematics of relativity into a picture so vivid that it has shaped how physicists think about space and time ever since. His name was Hermann Minkowski, and in the autumn of 1908, he stood before an audience of scientists in the city of Cologne and told them that space and time, as separate entities, were finished. They were, he said, doomed to fade away into mere shadows. Only a kind of union of the two would preserve an independent reality. Minkowski was a mathematician, not a physicist, and he had known Einstein years earlier, when Einstein was a student at the Swiss Federal Polytechnic in Zurich. By all accounts, Einstein had not been a particularly diligent student, at least not in the formal sense. He skipped lectures, relied on the notes of a friend, and devoted his attention to the problems that interested him rather than the ones assigned by his professors. Minkowski, who taught mathematics at the Polytechnic, had not been impressed. He later described the young Einstein as a lazy dog, but Minkowski had been watching from a distance as Einstein's 1905 paper circulated through the scientific world. The paper on the electrodynamics of moving bodies, with its strange conclusions about time and simultaneity, caught his attention, and Minkowski saw something in it that Einstein himself had not fully articulated. He saw that the equations of special relativity were not merely a set of transformation rules for converting measurements between reference frames. They were the description of a geometry, a four-dimensional geometry in which space and time were woven together into a single fabric. The lecture in Cologne, delivered on the 21st of September, was Minkowski's attempt to explain this vision. He called his framework the absolute world, and he introduced a new vocabulary to describe it. The history of a particle, traced through space-time, was not a sequence of positions at successive moments. It was a single curve, a world line, extending through the four-dimensional manifold. The world line of a person at rest was a vertical line, pointing straight up through time. The world line of a person in motion was tilted, angled away from the vertical, and the world line of a beam of light was tilted at exactly 45 degrees, the boundary between what could be reached and what could not. In Minkowski's picture, the universe was not a stage on which events unfolded one after another. It was a landscape, a static four-dimensional structure in which every event that had ever happened or ever would happen already existed. But the past was not gone. The future was not yet to come. They were simply elsewhere, other regions of the same unchanging manifold. Time, in this picture, was not something that flowed. It was a direction, like up or north, and different observers moved through the manifold along different paths, each one carrying a different notion of what was happening now. This was the block universe, though Minkowski did not use that phrase. It was a picture of reality as a single, complete, timeless whole, in which the passage of time was not a feature of the universe, but a feature of the observer's perspective. Each observer sliced through the block along a different plane of simultaneity, and each slice revealed a different cross-section of events. What one observer called the present, another observer called a mixture of past and future, and yet the block itself, the totality of all events, was the same for everyone. Minkowski's lecture lasted less than an hour. He was 44 years old, at the height of his intellectual powers, and he must have known that he was presenting something profound. The response from the audience was respectful but muted. The full significance of what he had proposed would take years to sink in. Einstein himself, when he first heard about Minkowski's geometric interpretation, was dismissive. He called it superfluous learnedness, a mathematical flourish that added nothing to the physics. He would later change his mind. When Einstein turned his attention to gravity, when he began the long struggle that would lead to general relativity, he found that Minkowski's geometry was not superfluous at all. It was essential. The four-dimensional framework was the only language in which the new theory could be written. But Minkowski did not live to see that vindication. 4 months after his lecture in Cologne, in January of 1909, he was struck by appendicitis. The appendix ruptured and the infection spread. He died at the age of 44, leaving behind a widow and 2 daughters, and a vision of the universe that would outlast him by more than a century. The block universe is not a comfortable idea. It sits uneasily with the way we experience time, with the sense that the present moment is special, that the past is fixed and the future is open. In the block, there is no special moment. Every moment is equally real, equally present, equally there. The distinction between past, present and future is, as Einstein would later write in a letter of condolence to the family of a deceased friend, only a stubbornly persistent illusion. And yet the geometry is precise. The world lines are real, in the sense that they describe the actual paths of objects through space-time. The light cones are real, in the sense that they define the boundaries of causation. The space-time interval is real, in the sense that it is the same for every observer. These are not metaphors or approximations. They are the structure of the world as relativity reveals it. Consider your own world line. It begins at a particular event, the moment of your birth, at a particular location in space. It extends through time, curving and bending as you move from place to place, but always pointing generally upward toward the future. Every moment of your life, every experience you have ever had, every breath you have ever taken is a point on that world line. And in the block universe picture, every one of those points still exists. The moment of your first step is still there, a fixed location in the four-dimensional manifold. The moment you learn to read is still there. The moment you first understood that time was strange is still there. None of them have vanished. None of them have faded away. They are simply elsewhere, in a region of space-time that you can no longer reach, because your world line has moved on. This is the picture that the mathematics of relativity suggests. It is not a proof. It is not a conclusion that follows inevitably from the equations. There are other interpretations, other ways of reading the same formalism. But the block universe is the most straightforward reading, the one that takes the geometry at face value. And it raises a question that is not scientific but philosophical, a question about what it means for something to be real. If every moment of your life still exists, if the past is not gone but simply elsewhere, then what is it that moves? What is it that distinguishes the present moment from all the others? The block itself does not change. It cannot change, because change requires time, and the block contains all of time within it. The world lines do not move through the block. They are the block, or at least part of it. And yet here you are, reading these words, experiencing this moment as now, as present, as the leading edge of something. The answer, if there is one, may not lie in physics at all. It may lie in the nature of consciousness, in the way that a mind embedded in a world line experiences its own existence. The block does not explain why you feel like you are moving through time. It does not explain why the present moment feels different from memory or anticipation. It simply says that, from the outside, from the God's eye view of the four-dimensional manifold, there is no difference. Every moment is equally real. Every moment is equally now for the observer who is there. And so we return once more to the breakfast. The daughter sitting at the table watching her father eat. The moment is still there, in the block. The world line of the father passes through it. The world line of the daughter passes through it. They are both still there, in that configuration, in that arrangement of matter and light and love. The moment has not vanished. It has simply become elsewhere. And the daughter, moving along her own world line, can no longer reach it. She can remember it. She can carry it with her, encoded in the structure of her brain, which is itself part of her world line. But she cannot return to it, because world lines do not loop back. They move forward, always forward, into regions of space-time that were once the future, and are now the present, and will soon be the past. This is the shape of existence that Minkowski revealed. Not a river flowing from past to future, but a landscape, vast and still, in which every moment has its place. The geometry is beautiful in its way. It is also unsettling. It suggests that the passage of time, the thing we feel most intimately, may not be a feature of the universe at all. It may be a feature of us, of the way consciousness moves along a world line, experiencing each moment as it arrives, and then leaving it behind. The world line tells where you go, but it does not, by itself, tell how long the journey takes. That distinction, subtle and easy to miss, is the key to one of relativity's strangest predictions. Two world lines can begin at the same event and end at the same event, tracing different paths through space-time, and the proper time elapsed along those paths, the time actually experienced by a traveller moving along the world line, can be different. Not different in the sense that clocks might disagree about simultaneity, but different in the sense that one clock, at the end of the journey, will have ticked fewer times than the other. One traveller will have aged less. One life will have been shorter, measured in heartbeats and breaths, even though both lives occupy the same span of history. This is not a defect in the clocks. It is not an illusion. It is a fact about the geometry of space-time, as fundamental as the fact that a straight line is the shortest distance between 2 points in Euclidean space. In space-time, the straight world line, the one that never accelerates, never changes direction, is the longest in terms of proper time. The curved world line, the one that bends, is shorter. Consider two siblings. They are born on the same day, in the same hospital, and for the first 20 years of their lives their world lines run nearly parallel side by side through the ordinary space-time of a quiet town. Then one of them leaves. She boards a spacecraft capable of travelling at a significant fraction of the speed of light, say 80% of light speed, and she departs. The journey is long. She travels outward, away from Earth, for what her own clock measures as 5 years. Then she turns around, decelerating and then accelerating in the opposite direction, and she travels back, another 5 years by her clock. When she steps off the spacecraft, she's 30 years old. 10 years have passed for her. But when she sees her sibling, the one who stayed behind, she finds that he is 50 years old. 20 years have passed on Earth. The traveller has aged half as much as the one who stayed home. She is, by every measure that matters, cellular, biological, experiential, younger than her twin. This is the twin paradox, and it is not a paradox at all. It is a straightforward consequence of the relativity of time. The confusion arises because it seems at first glance as though the situation should be symmetrical. From the traveller's perspective, isn't the earthbound twin the one who is moving? Shouldn't he be the one who ages more slowly? The answer is no, and the reason is acceleration. The travelling twin does not remain in a single inertial frame. She accelerates when she departs. She decelerates and then accelerates again when she turns around. She decelerates once more when she arrives home. Each of these accelerations is a change of reference frame, and that change breaks the symmetry. The earthbound twin, by contrast, remains in a single inertial frame for the entire duration. He does not turn around. His world line in the spacetime diagram is a straight vertical line. Hers is bent, curved by the accelerations, and in the geometry of spacetime the curved path accumulates less proper time. This is not merely a thought experiment, it is a prediction that can be tested, and it has been tested many times, with results that align precisely with Einstein's equations. The first definitive test came in 1971 when two experimenters, Joseph Haefel, a physicist, and Richard Keating, an astronomer with access to extremely precise clocks, decided to take relativity on a journey. They obtained 4 cesium beam atomic clocks, each about the size of a suitcase and weighing roughly 60 pounds. These clocks were extraordinarily accurate, capable of measuring time to within a few nanoseconds. They were also extraordinarily expensive, about $17,000 apiece, and extraordinarily delicate. They could not be subjected to the rough handling of cargo holds, and so Haefel and Keating bought seats for them. The clocks flew as passengers strapped into their own seats, each one travelling under the name Mr. Clock. The plan was simple in outline, intricate in execution. They would fly the clocks around the world, first eastward and then westward, on ordinary commercial airline flights. They would compare the clocks, after each journey, to reference clocks that had remained on the ground at the United States Naval Observatory in Washington. The prediction, according to both special and general relativity, was that the flying clocks would show a measurable difference. Special relativity predicted that the motion of the aircraft, relative to the surface of the Earth, would cause time dilation. The moving clock should tick more slowly, and therefore fall behind. But general relativity added a complication. The aircraft flew at altitude, roughly 10 kilometers above the Earth's surface, where the gravitational field is slightly weaker. In a weaker gravitational field, time runs faster. The two effects, kinematic time dilation from motion and gravitational time dilation from altitude, would partly cancel each other out, but not completely. The net result depended on the direction of travel. When flying eastward, the aircraft is moving in the same direction as the Earth's rotation, so its velocity relative to the centre of the Earth is higher. The kinematic effect dominates, and the flying clock should lose time. When flying westward, the aircraft is moving against the Earth's rotation, so its velocity relative to the centre of the Earth is lower. The gravitational effect dominates, and the flying clock should gain time. The magnitudes involved were tiny. The predictions were 59 nanoseconds lost for the eastward journey, 273 nanoseconds gained for the westward journey. A nanosecond is a billionth of a second. The entire effect over a journey that took days was less than a third of a microsecond, and yet it was measurable if the clocks were good enough. The eastward journey began on October the 4th, 1971. The clocks flew from Washington to London, then to Frankfurt, Beirut, New Delhi, Bangkok, Hong Kong, Tokyo, Honolulu, and back to Washington. The total elapsed time was 65.4 hours, of which 41.2 hours were spent in flight. When the clocks were compared to the reference clocks on the ground, they had lost 59 nanoseconds, give or take 10 nanoseconds. The westward journey began on October the 13th. The route ran from Washington to Los Angeles, Honolulu, Guam, Okinawa, Hong Kong, Bangkok, New Delhi, and back. The total elapsed time was 80.3 hours. When the clocks returned, they had gained 273 nanoseconds, give or take 7. Both results agreed, within the experimental uncertainty, with the predictions of relativity. Time had slowed down for the eastward clocks. Time had sped up for the westward clocks. The effect was real. The Haffel-Keating experiment is sometimes presented as a curiosity, a confirmation of an exotic theory with no practical consequences. But that is not true. The same effects that Haffel and Keating measured in 1971 are essential to the functioning of the global positioning system. A GPS receiver in your pocket determines your location by comparing the arrival times of radio signals from multiple satellites orbiting overhead. The satellites orbit at an altitude of roughly 20,000 kilometers, traveling at a speed of about 14,000 kilometers per hour. Both the velocity and the altitude affect the rate at which the onboard clocks tick. Special relativity, accounting for the velocity, predicts that the satellite clocks should run slow by about 7 microseconds per day. General relativity, accounting for the weaker gravitational field at altitude, predicts that the satellite clocks should run fast by about 45 microseconds per day. The net effect is that the satellite clocks gain roughly 38 microseconds per day relative to clocks on the ground. If this effect were not corrected, if the satellite clocks were allowed to drift, the accumulated timing error would translate into a positioning error of about 10 kilometers per day. Within a week, GPS navigation would be useless. The system works because engineers program the satellites to tick at a slightly slower rate than they would naturally, compensating in advance for the relativistic effects. Every time you check a map on your phone, you're relying on the fact that time is not universal. The twin paradox is no longer hypothetical. In 2015, astronaut Scott Kelly began a year-long mission aboard the International Space Station. His identical twin brother Mark remained on Earth. When Scott returned in 2016, after 340 days in orbit, travelling at roughly 28,000 kilometers per hour, he had aged slightly less than his brother. The difference was small, about 8.5 milliseconds, but it was real, measurable, and consistent with the predictions of relativity. The twin who travelled came home younger. The question that the twin paradox raises is not whether time dilation happens. It does. The question is what it means. If the travelling twin's life is shorter, measured in experienced time, does that mean that fewer moments of her life exist in the block universe? Or does it mean that her world line, though shorter in proper time, is just as real, just as complete, as her siblings? The geometry suggests the latter. Each twin traces a path through space-time. One path is longer, one is shorter, but both are paths, both are world lines, and both are part of the block. The traveller's life is not incomplete. It is simply a different shape. This is where the abstraction becomes difficult to hold. We are accustomed to thinking of a life as a duration, a span of time that accumulates from birth to death. But in the block universe, a life is not a duration. It is a structure, a four-dimensional object with a beginning and an end and a shape in between. The travelling twin's life is a bent world line, The Earthbound twins' life is a straight one. Both lives are complete. Both lives are real. The difference is not in their existence, but in their length, measured in the only way that length can be measured along a world line, by the proper time accumulated along the path. And if that is true, if a life is a shape, a completed shape, with every moment of it existing simultaneously in the four-dimensional manifold, then the question shifts. It is no longer a question about whether time passes differently. It is a question about whether a person's entire lifespan, from birth to death, can be understood as something that simply is, rather than something that unfolds. The idea is easier to accept when we think about objects. A table exists. It has a beginning in time, the moment it was built, and an end in time, the moment it will be destroyed, and in between it occupies a region of space-time. The four-dimensional shape of the table is the table's world line, and we do not find it strange to say that the table, as a four-dimensional object, exists in its entirety, even though we can only see a three-dimensional slice of it at any given moment. But when we think about people, about ourselves, the idea becomes uncomfortable. If your life is a four-dimensional structure with every moment of it already laid out in the block, then in what sense are you alive right now? In this moment? In what sense is the future still open? The block universe does not answer that question. It only makes it sharper. The experiment that first proved time dilation was small and modest and cost $8,000, most of which went toward airline tickets. The experiment that confirmed the block universe, if we are willing to call it that, was far older and far grander, and it had nothing to do with clocks. It had to do with light and gravity and a total eclipse of the sun. Albert Einstein completed the general theory of relativity in November of 1915, after 8 years of struggle. The theory extended the relativity of motion to include acceleration and gravity, and it replaced the fixed, flat space-time of special relativity with something far stranger, a space-time that could bend. Mass and energy, according to the field equations, curve the geometry of space-time itself. A planet does not orbit the sun because it is pulled by a force. It orbits because it is following the straightest possible path, a geodesic, through a space-time that has been warped by the sun's mass. Gravity, in this picture, is not a force at all. It is the shape of the stage. The theory made several predictions that differed from Newtonian gravity, but the differences were tiny, detectable only in extreme conditions. One prediction concerned the orbit of Mercury, which precesses, shifts slightly with each orbit, in a way that Newtonian mechanics could not fully explain. General relativity explained it exactly. Another prediction concerned the bending of light. Newton's theory predicted that light, if it had mass, would be deflected slightly by the sun's gravity. Einstein's earlier incomplete calculation from 1911 had agreed, but the full theory of general relativity, published in 1915, predicted a deflection twice as large, 1.75 arcseconds for a ray of light passing just at the edge of the sun. An arcsecond is 1/3600th of a degree. The predicted deflection was tiny, but it was measurable if you could see stars near the sun, and you can see stars near the sun only during a total solar eclipse. The astronomer Frank Dyson, who served as Astronomer Royal of England, realised that an opportunity was coming. On May 29th, 1919, there would be a total eclipse, and the sun would be positioned directly in front of the Hyde star cluster, a dense grouping of bright stars. The eclipse would last nearly 7 minutes, the longest total eclipse in over 5 centuries. If expeditions could be sent to locations along the path of totality, and if photographs could be taken during the eclipse showing the positions of the stars near the sun, and if those positions could be compared to photographs taken of the same stars when the sun was elsewhere in the sky, then the deflection could be measured. If the deflection matched Einstein's prediction, it would be the first confirmation of general relativity. If it did not, the theory would be in serious trouble. Dyson organised 2 expeditions. One, led by Arthur Eddington, a mathematician and astronomer at Cambridge, would travel to the island of Principe, off the west coast of Africa. The other, led by Andrew Crommelin and Charles Davidson of the Royal Greenwich Observatory, would travel to Sobral, a town in northern Brazil. Both expeditions carried telescopes, cameras and photographic plates. Both faced difficulties. The weather at Principe was uncertain. Clouds rolled in and out during the eclipse, and Eddington managed to capture only a handful of usable plates. The weather at Sobral was clear, but one of the telescopes, the primary instrument, suffered from thermal distortion and produced blurred images. The backup telescope, smaller and simpler, performed better. When the expeditions returned and the plates were analysed, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6, 1919. The measurements from Sobral, using the backup telescope, gave a deflection of 1.98 arcseconds, with an uncertainty of about 0.12 arcseconds. The measurements from Principe gave 1.61 arcseconds, with a larger uncertainty. Both values were consistent with Einstein's prediction of 1.75 arcseconds. Neither was consistent with the Newtonian prediction of 0.87 arcseconds. The conclusion, announced to a packed hall and reported in newspapers around the world the following day, was that general relativity had been confirmed. Einstein, who had been relatively unknown outside of physics, became an international celebrity overnight. There has been controversy in the decades since about whether Eddington's analysis was entirely objective. Some of the plates from Sobral were discarded as defective, and critics have suggested that the selection was influenced by the desire to confirm Einstein's theory. Subsequent reanalyses using modern techniques have generally supported the original conclusion, but the debate lingers. What is not in doubt is the physical principle. Light does bend near the sun. The deflection has been measured many times since 1919, using radio waves from distant quasars, and the measurements agree with general relativity to within a fraction of a percent. Spacetime is curved by mass. The stage is not fixed, and that deepens the puzzle. If spacetime is a four-dimensional block, static and unchanging, then how can it also be curved? The answer is that the curvature is part of the block. The geometry of spacetime is not imposed from outside. It is determined by the distribution of mass and energy within the spacetime itself. The presence of the sun curves the spacetime around it, and that curvature is part of the four-dimensional manifold. The curvature does not change, in the sense that the block itself does not change. It is simply part of the shape. But the curvature is dynamic in another sense. It responds to the motion of matter. If the sun were to suddenly vanish, the curvature would change, and that change would propagate outward at the speed of light, like ripples on a pond. The change is not instantaneous. It takes time for the geometry to adjust, and that suggests that the block, if it exists, is not built all at once. It is built or revealed moment by moment as the equations of general relativity determine how the geometry evolves from one slice to the next. This is where the block universe picture becomes most difficult to reconcile with experience. If the future is already laid out, already determined by the geometry, then in what sense is the geometry evolving? If the curvature at every point in space-time is part of the block, then the ripples that propagate outward from a change in mass are not spreading through time. They are simply there, part of the structure, and our sense that they are moving as an artifact of the way we, embedded in our world lines, experience the manifold. The mathematics allows both interpretations. You can treat space-time as a completed four-dimensional structure in which every event, past and future, is equally real. Or you can treat it as a three-dimensional space evolving in time, in which the future does not yet exist and is brought into being by the unfolding of physical law. The equations do not distinguish between these views. They describe the relationships between events, the geometry that connects them, but they do not tell you which events are real right now, because they do not contain a variable for now. Relativity, taken seriously, suggests that the question itself may not have an answer. The block is there, or it is not, and no experiment can tell the difference, because every experiment is itself part of the block. At the edge of the horizon, consider, for a moment, what happens when the curvature of space-time becomes not merely measurable but extreme. Near the surface of a neutron star, or at the boundary of a black hole, gravity is not a subtle bending of trajectories but a profound reshaping of time itself. The closer you move to a massive object, the more slowly time passes for you, relative to someone far away. This is not an illusion, not a malfunction of your clock. It is a consequence of the geometry Einstein described, carried to its most unsettling conclusion. The effect is called gravitational time dilation, and it was implicit in the equations of general relativity from the beginning, though its full significance took years to appreciate. The idea is simple to state and difficult to absorb. A clock ticking at sea level runs more slowly than an identical clock ticking on a mountaintop, because the clock at sea level is deeper in Earth's gravitational well. The difference is tiny, a few tens of nanoseconds per day, but it is measurable. In 1959, two physicists at Harvard, Robert Pound and Glenn Rebka, confirmed this by sending gamma rays up and down a tower in the Jefferson Physical Laboratory. The tower was only 22.5 meters tall, but the shift in frequency, caused by the change in gravitational potential, was exactly what Einstein's equations predicted. The gamma rays climbed out of the gravitational well and lost energy, their frequency dropping by a part in 10 to the 15th. The experiment was delicate, relying on a phenomenon called the Nussbauer effect to measure the shift, but the result was unambiguous. Time itself runs at different rates at different heights in a gravitational field. The effect is not limited to towers or mountains. Every time you stand up, the top of your head is aging slightly faster than your feet. The difference is far too small to measure without atomic clocks, and it averages out over a lifetime, but it is real, and it scales with the strength of gravity. Near the surface of a neutron star, where gravity is so strong that the escape velocity approaches a significant fraction of the speed of light, the dilation becomes dramatic. A neutron star is what remains after a massive star collapses, its core compressed to densities beyond anything achievable in a laboratory. The radius of a typical neutron star is about 10 to 12 kilometers, and the mass is between 1 and 2 times the mass of the Sun. That combination produces a gravitational field so intense that the space-time around it is warped almost to the breaking point. A clock on the surface of a neutron star would tick roughly 1.4 to 1.7 times more slowly than a clock far away in flat space, depending on the star's exact mass and radius. An hour on the surface would correspond to an hour and a half or more for a distant observer. And if you could stand on that surface looking up at the stars, you would see the universe outside running visibly faster, entire days passing in what felt like hours. But even a neutron star is not the most extreme case. The equations of general relativity permit a solution, discovered in 1916 by a German physicist named Karl Schwarzschild, in which the curvature becomes so severe that time, from the perspective of a distant observer, appears to stop altogether. Schwarzschild was serving in the German army during the First World War when he derived the solution, and he sent it to Einstein in a letter from the Russian front. Einstein was astonished by the result. Schwarzschild had found an exact solution to the field equations for a spherically symmetric, non-rotating mass, and the solution predicted something strange. There was a critical radius, now called the Schwarzschild radius, at which the geometry changed character. For a mass concentrated within that radius, the curvature became so intense that nothing, not even light, could escape from within it. The Schwarzschild radius depends on the mass of the object. For the Sun, it is about 3 kilometers. For Earth, it is about 9 millimeters, as long as the object's physical radius is larger than its Schwarzschild radius. The solution describes the space-time outside the object, and the interior is determined by the distribution of matter within. But if the object is compressed to within its Schwarzschild radius, the solution predicts the formation of a boundary in space-time itself, a surface from which no light, no signal, no information can escape. That boundary is called the event horizon, and the region within it is what we now call a black hole. Einstein himself was uncomfortable with the idea. He published a paper in 1939 arguing that physical processes would prevent the formation of black holes, that the collapse of matter would be halted before the event horizon could form. He was not alone in his skepticism. Many physicists regarded the Schwarzschild solution as a mathematical curiosity, a pathology of the equations rather than a physical prediction. But the mathematics was unambiguous, and as astronomers discovered objects in the universe that could not be explained by any other means, the resistance faded. By the late 20th century, black holes were no longer speculative. They were observed indirectly through the behavior of gas and stars near them, through the X-rays emitted by infalling matter, through the gravitational waves produced when two black holes merged. And in 2019, an international collaboration of radio astronomers succeeded in producing an image of one. The image was released on April 10, 2019, and it showed the silhouette of a black hole at the centre of a galaxy called Messier 87, located about 55 million light-years from Earth. The black hole itself is invisible, as it must be, because no light escapes from within the event horizon. What the image shows is the shadow of the event horizon, a dark disk outlined by the glowing gas of the accretion disk that surrounds it. The gas, heated to billions of degrees as it spirals inward, emits radio waves, and those waves trace the shape of the space-time around the black hole. The shadow is larger than the event horizon itself, about 2.6 times the Schwarzschild radius, because the intense gravity bends the light from the accretion disk, creating a photon sphere where light can orbit the black hole before either falling in or escaping. The image is a direct portrait of curved space-time, a confirmation of Einstein's equations in a regime where the curvature is extreme. The black hole was given a name by Hawaiian cultural practitioners who chose the word Pauehi, meaning the adorned fathomless dark creation. The name is fitting. The object is fathomless in a literal sense. Once matter crosses the event horizon, it is lost to the outside universe. No signal can return from within. And the darkness is not simply the absence of light. It is the absence of any possibility of light. The event horizon is not a physical surface, not a barrier you could touch. It is a boundary in space-time itself, a place where the geometry changes in such a way that all future directed paths, all world lines that cross it, lead inward. From the perspective of someone falling toward the horizon, nothing unusual happens at the moment of crossing. There is no jolt, no sensation, no locally detectable change. The falling observer's clock ticks at the same rate it always did. But from the perspective of a distant observer, the falling object appears to slow down as it approaches the horizon, its light red-shifting, dimming, until it seems to freeze just above the surface, never quite crossing. The distant observer never sees the object fall in. Time, as measured from a distance, appears to stop at the event horizon. This is gravitational time dilation carried to its logical extreme. The closer you are to the horizon, the more slowly time passes for you, relative to someone far away. At the horizon itself, from the perspective of the distant observer, time does not pass at all. The infalling object is, in that sense, suspended forever at the moment of crossing, though the object itself, following its own world line, experiences no such suspension. It crosses the horizon and continues inward, toward the singularity at the centre, where the curvature becomes infinite and the equations of general relativity break down. The contradiction between these two perspectives, the distant observer and the infalling one, is not a failure of the theory. It is a consequence of the relativity of simultaneity. There is no universal now, no single present moment shared by both observers. The distant observers now and the infalling observers now are different slices through space-time, and the horizon is the place where those slices diverge most dramatically. The image of the black hole in Messier 87 was produced by the Event Horizon Telescope, a collaboration of more than 300 researchers and 8 ground-based radio telescopes, coordinated to act as a single instrument the size of the Earth. The telescopes, located in places as distant as Chile, Hawaii and the South Pole, observed the black hole simultaneously over several nights in April 2017. The observations were synchronized using atomic clocks, the same technology that corrects for relativistic effects in GPS satellites, and the data were combined using a technique called interferometry, which allowed the collaboration to achieve the resolution necessary to image the shadow of the event horizon. The black hole itself is enormous, with a mass about 6.5 billion times the mass of the Sun, and it rotates, dragging space-time around it in a phenomenon called frame dragging. The rotation parameter is estimated to be about 0.9, meaning the black hole is spinning close to the maximum rate permitted by general relativity. The rotation affects the shape of the space-time around it, described by a solution to Einstein's equations discovered by the New Zealand mathematician Roy Kerr in 1963, and it influences the appearance of the accretion disk, which is brighter on one side than the other because of the Doppler effect from the gas moving at relativistic speeds. What is remarkable about the image is not simply that it confirms the existence of black holes, though it does, but that it confirms the structure of space-time in a regime where the predictions of general relativity were, until recently, untestable. The shadow is the size and shape that Einstein's equations predict. The curvature is as the geometry requires, and the fact that we can see the shadow at all is a consequence of the way light behaves in curved space-time, bending around the black hole, some of it captured, some of it deflected into our line of sight. The image is, in a deep sense, a map of time. The dark centre is not simply where light cannot escape, it is where time, from the perspective of the outside universe, has slowed to a standstill. And the glowing ring around it is where time is running at different rates depending on the distance from the horizon, each photon carrying information about the geometry of the space-time it travelled through. Gravitational time dilation is measurable even here on Earth, in less dramatic circumstances. Atomic clocks at different altitudes tick at different rates, a difference that must be accounted for in the synchronization of GPS satellites. The satellites orbit at an altitude where gravity is weaker, and their clocks run faster than clocks on the ground by about 45 microseconds per day. Combined with the slower rate caused by their orbital motion, a special relativistic effect, the net difference is about 38 microseconds per day, and if that difference were not corrected, GPS positioning would drift by kilometers within a matter of days. The correction is built into the system. The satellite clocks are set to tick slightly more slowly before launch, so that once in orbit accounting for both gravitational and kinematic effects, they stay synchronized with ground-based clocks. Every time you use a GPS device to find your way, you are relying on the fact that time runs at different rates in different places, and that those rates can be predicted and corrected using Einstein's equations, the trial of the present. And so, we arrive at the question that has been waiting beneath all of this. If time is relative, if simultaneity is observer-dependent, if the geometry of space-time determines the rate at which clocks tick, then what does it mean to say that the present moment is real and the past is gone? Relativity does not require you to abandon the idea of a present. It requires you to acknowledge that your present is not universal, that someone moving differently or standing at a different height in a gravitational field has a different present, and that there is no experiment, no measurement, no physical principle that can determine which of you is right. The question is no longer scientific, it is metaphysical, and it has been argued over in increasingly precise terms for more than a century. The philosopher who set the terms of the debate most clearly was an Englishman named John MacTaggart Ellis MacTaggart, who taught at Trinity College, Cambridge, in the early decades of the 20th century. MacTaggart was an idealist, a follower of Hegel, and he believed that time, as we ordinarily understand it, is unreal. He published his argument in a paper in 1908, the same year that Minkowski gave his lecture on space-time, and the argument has been debated ever since. MacTaggart distinguished between two ways of describing the order of events in time. He called them the A series and the B series. The A series is the familiar tensed way of talking about time. Events are past, present or future, and these properties change. The event that is now present was once future and will soon be past. The B series, by contrast, is tenseless. Events are simply earlier than, simultaneous with, or later than other events, and these relations do not change. If event A is earlier than event B, it is always earlier, regardless of when you ask the question. McTaggart argued that the A series, the tensed series, is essential to time, because without the shifting of events from future to present to past, there is no genuine temporal passage, no real change. But he also argued that the A series is contradictory, because every event must be past, present, and future, and these properties are incompatible. The contradiction, he concluded, shows that time is unreal. Most philosophers rejected McTaggart's conclusion, but the framework he introduced, the distinction between tensed and tenseless descriptions of time, has shaped the debate ever since. The central question is whether the present moment has a special status, whether it is the only moment that is real, or whether all moments, past, present, and future, exist equally. The view that only the present is real is called presentism. It is close to common sense. The past is gone, the future has not yet happened, and all that exists is now. But presentism faces immediate difficulties when confronted with relativity. If simultaneity is relative, if there is no universal present, then what determines which events are real at any given moment? Your present and my present, if we are moving relative to each other, are different slices through space-time. Does reality shift depending on who is asking the question? And if so, which observer's present is the real one? Relativity offers no answer, because it denies that the question has any physical content. A second view, less intuitive but more accommodating to relativity, is called the growing block theory. It was defended by a philosopher named Charlie Dunbar Broad, who was a student of McTaggart's and published his account in 1923. The growing block theory holds that the past and present are real, but the future is not. Reality is a block that grows moment by moment as new events come into being. The past does not vanish. It remains fixed and unchanging as new layers are added to the present edge. The appeal of the growing block theory is that it preserves the sense that time passes, that new things come into existence, while also allowing that the past is not gone. But it too struggles with relativity. If the block grows, there must be a definite present moment at which the growth occurs, a boundary between what is real and what is not yet real. And relativity denies that such a boundary exists. The third view, and the one most consistent with the structure of relativity, is called eternalism. It is the view that all moments in time, past, present, and future are equally real. The four-dimensional spacetime manifold is not growing, not changing, not coming into being. It simply is. Your birth, your breakfast this morning, your death, all exist as events in the block, none more real than the others. The experience of the present, the feeling that now is special, is not an illusion exactly, but it is not a feature of reality. It is a feature of your perspective, of the way you, embedded in your world line, encounter the events around you. The present in this view is like the word here. It refers to a location in space-time, your location, but it does not imply that your location is the only one that exists. You would not claim that only the place where you are standing is real, and that everywhere else is gone or not yet arrived. Eternalism applies the same reasoning to time. The case for eternalism was argued most influentially by the American philosopher Hilary Putnam in a paper published in 1967. Putnam pointed out that relativity of simultaneity makes it impossible to maintain that only the present exists, because there is no fact of the matter about which events are present. If your present includes an event that my present does not, and we are both correct in our assessments, then the event must exist for you and not for me, and that is incoherent. The only consistent position, Putnam argued, is to accept that all events exist, regardless of when they occur relative to any particular observer. The argument has been refined and debated ever since, joined by similar arguments from the Dutch physicist Hilbert Ritdijk in 1966 and the philosopher Nicholas Maxwell in 1985, collectively known as the RPM arguments. The conclusion they reach is that if you take relativity seriously, if you accept that there is no universal now, then you are compelled to accept eternalism, to accept the block universe. Not all philosophers are convinced. Some have argued that relativity does not settle the metaphysics, that the equations describe relationships between events, but do not tell you which events are real. Others have proposed modified versions of presentism, or the growing block theory that attempt to make peace with relativity by redefining what is meant by the present. But the tension remains. The manifest image, the way time appears to us in experience, flowing from past through present into future, does not easily reconcile with the scientific image, the static, tenseless structure described by Einstein's equations. And yet both are correct in their own domains. You cannot deny that time feels like it flows, that the present seems immediate and real in a way the past and future do not. Nor can you deny that relativity, tested again and again, confirms that there is no universal now, no preferred moment, no frame of reference in which the present is uniquely defined. Eternalists argue that the experience of flow is a matter for psychology, not physics, that the feeling of nowness is something the brain constructs, not something the universe provides, and that may be true, but it does not make the feeling any less vivid, or the question any less urgent. And so we arrive at the deepest resistance, the objection that rises not from equations or philosophical arguments, but from the texture of lived experience itself. You feel time passing. You feel the present moment sliding away, replaced by another and another and another. You feel the future approaching like weather, uncertain and full of possibility, and you feel the past receding, fixed and unreachable, growing more distant with every breath. This is not a theory you hold about time. This is time as you know it, time as it presents itself to you in every waking moment, time as the medium in which your entire life unfolds, and the block universe asks you to believe that this feeling, this most intimate and constant feature of your existence, is somehow misleading, that the flow you experience is not a feature of the cosmos, but something your mind constructs from materials that do not, in themselves, flow at all. The challenge is worth taking seriously, because the feeling is not a minor phenomenon, it is woven into the fabric of consciousness. When you make a decision, you experience the future as open, as branching into possibilities that narrow down to a single outcome only when you act. When you remember the past, you experience it as closed, as something that happened and cannot be changed. When you anticipate the future, you feel uncertainty, and when you recall the past, you feel certainty, or at least the illusion of it. These asymmetries are not philosophical positions you have adopted. They are the way experience comes to you, unbidden, from the moment you wake until the moment you fall asleep. And they seem to point in a direction, to mark a difference between what has been and what will be, to carve time into regions with different ontological statuses. The past is done, the future is not yet, the present is happening. How can all of this be wrong? The answer, or at least the beginning of an answer, lies in a distinction that was first articulated clearly in the early 20th century by a physicist who understood both the geometry of space-time and the irreversibility of ordinary experience. Arthur Eddington was a British astrophysicist, the same Eddington who led the 1919 eclipse expedition that confirmed general relativity, and he spent much of his later career thinking about the relationship between the laws of physics and the world as we actually encounter it. In a series of lectures delivered in the late 1920s, Eddington introduced a phrase that has shaped the conversation ever since. He called it the arrow of time. The phrase is deceptively simple. An arrow points in a direction, and Eddington was observing that time, unlike space, seems to have a direction built into it. You can walk north or south, east or west, and the laws of physics do not care, but you cannot walk backward in time, and the universe seems to care very much about the difference between earlier and later. The arrow of time is the name for this asymmetry, the fact that time has a direction in a way that space does not. And Eddington was careful to distinguish between different senses in which time might have a direction. There is the psychological arrow, the feeling of flow and passage. There is the cosmological arrow, the fact that the universe is expanding and evolving. And there is the thermodynamic arrow, the tendency of systems to move from order to disorder, from low entropy to high entropy, from the improbable to the probable. The thermodynamic arrow is the one that connects most directly to the laws of physics, and it is the one that Eddington identified as the most fundamental. If you follow the arrow, he suggested, you find more and more of the random element in the state of the world. That is what it means to point toward the future. The past is more ordered, the future is more disordered, and the direction of increasing disorder is the direction of time. This is not a metaphor, it is a precise statement about the behavior of physical systems, grounded in the work of the Austrian physicist Ludwig Boltzmann, who had developed the statistical interpretation of entropy in the 1870s. Boltzmann understood something profound about the relationship between the microscopic and the macroscopic. At the level of individual atoms and molecules, the laws of physics are time-symmetric. If you filmed a collision between two billiard balls and played the film backward, the reversed collision would obey the same laws as the original. There is nothing in the fundamental equations of motion that distinguishes past from future, and yet at the level of everyday experience, time is anything but symmetric. Eggs break but do not unbreak. Ice melts but does not spontaneously freeze. Coffee cools but does not spontaneously heat up. These processes have a direction, and that direction is always the same, always pointing from order to disorder, from unlikely arrangements to likely ones. Boltzmann explained this asymmetry in terms of probability. A macroscopic state, like a glass of water with ice in it, corresponds to an enormous number of microscopic states, each one a particular arrangement of all the molecules in the glass. Some macroscopic states correspond to vastly more microscopic states than others. A glass of uniformly mixed water at room temperature corresponds to far more molecular arrangements than a glass with a neat ice cube floating in it. And since the laws of physics do not prefer any particular microscopic arrangement over any other, systems tend to evolve from less probable macroscopic states to more probable ones, simply because there are more ways to be in the more probable states. This is the origin of the second law of thermodynamics, the law that entropy tends to increase. It is not a law that forbids the ice from spontaneously reforming. It is a law that says such an event is so improbable as to be effectively impossible, given the number of molecules involved. The crucial point is that this explanation works in both directions of time. If the laws of physics are time-symmetric, then the tendency toward higher entropy should apply equally to the past and the future. A system in a low-entropy state should be surrounded by higher entropy states in both temporal directions. And yet this is not what we observe. We observe the past to be lower in entropy than the present, and the present to be lower in entropy than the future. The arrow of time points consistently in one direction, and that direction is the direction of increasing entropy. Why? The answer, as best as physicists can tell, lies not in the laws of physics themselves, but in the boundary conditions of the universe. The laws are symmetric, but the initial state was not. The universe began approximately 13.8 billion years ago in an extraordinarily low entropy state. The Big Bang was not a disordered explosion, but a highly ordered configuration, a state of remarkable uniformity and smoothness, from which all the structure we see today has since emerged. The galaxies, the stars, the planets, the complexity of life, all of it represents the universe unwinding from that initial improbability, moving from lower entropy to higher entropy, from order to disorder. The arrow of time is not written into the laws, it is written into the initial conditions, and if the initial conditions had been different, if the universe had begun in a high entropy state, there would be no arrow, no direction, no distinction between past and future. This is a strange conclusion. It means that the flow of time, the feeling of passage, the asymmetry between what has been and what will be, is not a fundamental feature of the cosmos, but a consequence of a particular fact about how the universe started. The laws of physics do not know which way time goes. The universe knows because it remembers its beginning. And you know because you are part of the universe, made of matter that has been evolving away from that initial state for billions of years. Your memories, your sense of the past, your anticipation of the future, all of these are possible only because entropy increases, only because there is a direction to the unfolding of physical processes. If entropy did not increase, you would not remember the past because memory itself is a physical process that requires the dissipation of energy, the increase of disorder somewhere in the system. The arrow of time is not something you perceive, it is something that makes perception possible. And here is where the block universe begins to come into focus in a new way. The eternalist does not deny that time has a direction. The block is not a frozen, undifferentiated manifold in which all moments are identical. The block contains structure, contains asymmetries, contains the fact that entropy is lower at one end than the other. The direction of time is real, in the sense that it is a feature of the geometry, a gradient in the entropy of the universe. What the eternalist denies is that this direction implies a flow, a movement of the present along the world line, a passage from past to future. The direction is there, but nothing is moving along it. You are not travelling through time, you are extended in time, a four-dimensional structure embedded in a four-dimensional manifold, and the feeling of passage is something your brain constructs from the asymmetries in your environment, from the fact that your memories point in one direction and your anticipations point in the other. This brings us to the mind itself, to the ordinary human construction of the present moment. Because if the arrow of time is a matter of entropy and initial conditions, the experience of now is a satire of neuroscience and psychology, and the experience is not as simple as it seems. Consider what happens when you perceive the present. Light enters your eyes, sound enters your ears, touch receptors fire in your skin, and all of this information travels along nerves to your brain, where it is processed, integrated, and assembled into a coherent experience. But the processing takes time. Visual information requires approximately 80 to 100 milliseconds to reach conscious awareness. Auditory information is slightly faster, but still not instantaneous. And the information from different senses does not arrive at the same time. Light travels faster than sound, but visual processing is slower than auditory processing, and the brain must somehow reconcile these differences, binding together signals that arrive at different moments into a single, unified experience of the present. The brain does this by constructing the present, not by passively receiving it. The experience of now is not a window onto the world as it is at this instant. It is a model, built from delayed and fragmentary information, smoothed and integrated into something that feels immediate and whole. The psychologist William James, writing in the 1890s, called this the specious present, the short duration of which we are immediately and incessantly sensible. The specious present is not a durationless instant, not a knife edge between past and future. It is a window, a span of time that the brain treats as a single moment, even though it is composed of events that occurred at slightly different times. James described it as a saddleback from which we look in two directions, perceiving a small portion of the past and a small portion of the future as part of a continuous now. The specious present has been studied extensively in the century since James wrote. Research into multisensory integration has shown that the brain uses temporal windows of several hundred milliseconds to bind together stimuli from different senses. If a sound and a flash of light occur within this window, they are perceived as simultaneous, even if they are not. If they fall outside the window, they are perceived as separate events. The brain is constantly making judgments about what belongs together, what counts as the same moment, and these judgments are not infallible. They can be fooled by illusions, altered by attention, shifted by context. The present is not given to you, it is constructed by you, moment by moment, from the raw materials of sensation and memory, and the construction is predictive, not merely reactive. The brain does not wait passively for the world to announce itself. It anticipates, models, and predicts, using past experience to fill in gaps and smooth over delays. When you watch a moving object, your brain is not simply registering where the object is, it is predicting where the object will be, compensating for the lag in processing, aligning your perception with the world as it is likely to be by the time you respond. This is why you can catch a ball, why you can follow a conversation, why the world seems continuous and coherent, even though the information reaching your brain is fragmented and delayed. The present you experience is not the present as it is the present as your brain predicts it to be. This has implications for the block universe that are both troubling and oddly comforting. If the present is a construction, if the feeling of now is something the brain assembles from memory and prediction, then perhaps the present is not something the universe contains at all. Perhaps it is something minds do, a way of organizing experience, a feature of consciousness rather than a feature of reality. The eternalist can point to this and say that the block universe is not denying something real. It is simply locating the experience of flow where it belongs, in the brain, in the mind, in this particular way that conscious creatures encounter the world. But this does not make the experience less vivid or less important. The construction of the present is not a trick, not a deception, not a failure of perception. It is the foundation of everything you are. Your sense of being here, now, in this moment, is what makes you a person rather than a collection of events. Your memories of the past and your anticipations of the future are not illusions to be dispelled. They are the texture of your life, the medium in which love and grief and hope and fear unfold. The patient who loses the ability to form new memories does not become a block universe philosopher, serene in the knowledge that all moments are equally real. The patient is lost, unmoored, unable to construct the present that gives life its shape. The person who grieves for someone they have lost is not comforted by the thought that the loved one still exists, somewhere in the block, at an earlier coordinate in space-time. The grief is real, the loss is real, and the feeling that something is gone is not a philosophical error. It is the price of being a creature embedded in time, a creature for whom the present matters, for whom the direction of the arrow is not just a gradient in entropy, but the difference between having someone and having lost them. And so we arrive at a tension that physics alone cannot resolve. The block universe is consistent with relativity, consistent with the absence of a universal now, consistent with the structure of space-time as Einstein described it. But it is not consistent with the way experience feels, with the openness of the future, with the sense that decisions matter, with the conviction that what happens next is not yet determined. And this brings us to the deepest challenge to the block universe, the challenge that comes not from philosophy or psychology, but from physics itself, from the other great revolution of the 20th century, the revolution that Einstein himself never fully accepted. Quantum mechanics describes a world that is, in certain respects, fundamentally different from the world of relativity. In relativity, the future is determined by the present. Given the state of the universe at any moment, the equations of general relativity predict, in principle, the state of the universe at any other moment. The block is fixed, eternal, unchanging. But in quantum mechanics, the future is not determined. The state of a system is described by a wave function, a mathematical object that encodes probabilities rather than certainties. When a measurement is made, the wave function appears to collapse, to jump from a superposition of possibilities to a single definite outcome. And the outcome is not predictable, it is genuinely random, not in the sense that we lack information, but in the sense that the information does not exist until the measurement occurs. This is the measurement problem, the central puzzle of quantum mechanics, and it has been debated since the theory was first formulated in the 1920s. The physicist Niels Bohr, one of the founders of quantum mechanics, developed what came to be called the Copenhagen interpretation, a framework that accepts the randomness as fundamental and refuses to ask what is happening before the measurement. In this view, the wave function is not a description of reality, but a tool for calculating probabilities. The question of what is really going on, of what the electron is doing before you look at it, is not a question that physics can answer. The measurement creates the outcome. Before the measurement, there is no outcome to describe. This view is deeply uncomfortable to many physicists, and it was deeply uncomfortable to Einstein. He famously objected that God does not play dice, that a theory which cannot tell you what is happening when you are not looking is incomplete. The debates between Einstein and Bohr, which began at the Solvay conference in 1927 and continued for decades, are among the most celebrated in the history of physics. Einstein proposed thought experiments designed to show that quantum mechanics was missing something, that there must be hidden variables underlying the apparent randomness. Bohr responded with arguments designed to show that the thought experiments failed, that the randomness was real and irreducible. The debate was never fully resolved in their lifetimes, and it has not been fully resolved since. One alternative to the Copenhagen interpretation was proposed in 1957 by a young American physicist named Hugh Everett in his doctoral thesis at Princeton. Everett suggested that the wave function never collapses at all. Instead, every time a measurement is made, the universe branches into multiple copies, one for each possible outcome. In one branch, the electron goes left. In another branch, the electron goes right. Both outcomes are real. Both branches exist, and the appearance of randomness is an illusion created by the fact that you, the observer, are also branching, and each copy of you sees only one outcome. This is the many worlds interpretation, and it is, in a certain sense, even more extravagant than the block universe. It is not just that all moments of time are equally real. All possible moments of time are equally real, an ever-branching tree of parallel realities, each one as concrete and definite as the one you happen to find yourself in. The many worlds interpretation is deterministic. The wave function evolves according to a single, unbroken equation, the Schrödinger equation, and there is no randomness, no collapse, no moment at which the future is created. In this sense, it is compatible with the block universe. The block is simply larger than you thought, containing not just one history but all possible histories, a vast and silent manifold of branching world lines. But in another sense, the many worlds interpretation introduces a kind of openness, a proliferation of futures that the simple block universe does not contain. Your future is not a single thread extending forward in time, it is a branching tree, and you do not know which branch you will find yourself on until you get there. Other interpretations take different approaches. Some, like the pilot wave theory developed by Louis de Broglie and later David Bohm, restore determinism by introducing hidden variables, particles with definite positions guided by the wave function. In this view, the randomness is only apparent, a consequence of our ignorance of the hidden variables, and the future is as fixed as it is in classical physics. Others, like the objective collapse theories, modify the Schrödinger equation to include a physical mechanism for collapse, a genuine moment at which the superposition resolves into a single outcome. In these views, the future is not fixed. It is created moment by the collapse of the wave function, and the block universe is not the right picture. The honest answer is that physics has not delivered a final verdict. Relativity strongly suggests that there is no universal present, that the distinction between past and future is not absolute, that the block universe is the correct picture of spacetime. But quantum mechanics introduces elements, indeterminacy, measurement, branching, that do not fit easily into the block. The two great theories of 20th century physics have not been unified, and the question of what time really is Whether the future is fixed or open, whether the present is real or constructed, remains one of the deepest unresolved questions in all of science. What can be said is this: the feeling of flow, the sense that time passes, the conviction that the future is open and the past is closed, is not evidence against the block universe. It is a feature of experience that needs to be explained whether or not the block universe is true. The arrow of time, the direction of increasing entropy, explains why experience has a direction, why memory points one way and anticipation points the other. The construction of the present, the specious present of psychology, explains why experience feels immediate, why the now seems special even if it is not. And the puzzles of quantum mechanics remind us that the story is not finished, that the relationship between mind and matter, between observation and reality, between the present and the possible, is still being written. And so the question remains, hovering at the edge of everything we know. If the block universe is true, if all moments of your life are equally real, if the past is not gone and the future is not unwritten, then what does it mean to be here, now, in this moment, feeling the present slip away? The physics does not answer this question. The physics describes a structure, a geometry, a manifold of events. But you are not a structure. You are a person, embedded in time, experiencing the world from a particular vantage point, constructing the present from memory and prediction, feeling the weight of the past and the uncertainty of the future. The block universe does not take this away from you. It simply places it in a larger context, a context in which your experience is one thread in a vast and silent tapestry, a tapestry that contains everything that ever was and everything that ever will be, and in which the present moment, your present moment, is not the only moment that is real. The room where every moment remains. There is a way to bring all of this together, to make the abstraction concrete, to feel the weight of what relativity actually claims about the structure of time. It requires imagining a single room, a single moment, and then asking what it means for that moment to be present, or past, or anything at all. Picture a room in a house somewhere on Earth. It is evening. A daughter sits at her father's bedside. He's old and he's dying and she's holding his hand. Outside the window the world continues, oblivious. Cars pass on the street. Somewhere a dog barks. The light from the lamp on the bedside table is warm and the room smells faintly of the medication, and the tea she brought him hours ago, now cold in the cup. They are talking quietly about small things. She reminds him of a breakfast they shared when she was 10, a morning when he made pancakes and burned the first batch and they laughed about it, and he nods, and his eyes are distant, and she does not know if he remembers or if he is simply being kind. And then, after a while, he stops talking, and his breathing changes, and she knows, without anyone telling her, that this is the moment, the last moment, the one she will carry for the rest of her life, now. Is this moment present? Is it happening now? If you are sitting in that room, the answer feels obvious. Yes. Of course it is now. It is the only now there is. The breakfast when she was 10 is gone, years in the past, a memory that exists only in her mind and in whatever faint configuration of neurons still encodes it. The funeral that will happen in 3 days is not yet real. It has not happened. The present is this room, this breath, this hand. But relativity does not allow this. Relativity does not allow a universal now, a cosmic knife that cuts cleanly through space-time and separates the present from the past and the future. The reason is the relativity of simultaneity, the same principle that emerged from Einstein's thought experiments in 1905, the same principle that says that observers moving at different speeds will disagree fundamentally and irreconcilably about which events are happening at the same time. Imagine that at the same moment the daughter is sitting at her father's bedside, a spacecraft is passing Earth at a significant fraction of the speed of light. Not absurdly fast, not near the speed of light itself, but fast enough that relativistic effects are measurable. Say, 20% of the speed of light, which is roughly 60,000 kilometers per second, faster than anything we have ever built but not unimaginable, given enough time and enough energy. The spacecraft is carrying an observer, someone with a clock and a ruler, and all the tools necessary to measure space-time, and this observer is moving relative to Earth, moving in such a way that their notion of simultaneity, their plane of present events, is tilted relative to the daughter's. The tilt is described mathematically by the Lorentz transformation, the same set of equations that governs time dilation and length contraction, the equations that Einstein derived in his 1905 paper. The transformation tells you how to translate coordinates from one inertial frame to another, how to take an event that one observer calls simultaneous with their present moment, and determine when that event occurs in another observer's frame. And the result for observers moving at relativistic speeds is that events that are simultaneous for one observer are not simultaneous for another. The disagreement is not a matter of measurement error or signal delay, it is a matter of geometry. The two observers are cutting through space-time along different axes, and the slices they obtain do not line up. For the observer on the spacecraft moving at 20% of the speed of light relative to Earth, the plane of simultaneity is tilted. Events that the daughter would call present, events happening right now in her frame, are in the spacecraft observer's past or future, depending on the direction of motion. And the tilt is not small. For distant events, events happening far from Earth, the tilt can amount to hours, days, even years of disagreement about what is happening now. The example that makes this vivid is sometimes called the Andromeda paradox, a thought experiment discussed by the physicist and mathematician Roger Penrose in his book The Emperor's New Mind, published in 1989. Andromeda is a galaxy, a spiral of several 100 billion stars, located roughly 2.5 million light-years from Earth. It is the nearest large galaxy to our own, and on a clear night far from city lights you can see it as a faint smudge in the constellation Andromeda, a patch of light that has been travelling toward you for 2.5 million years. Now imagine two people walking past each other on a street on Earth. One is walking toward Andromeda, the other away from it, and they are moving relative to each other at a leisurely pace, say 3 miles per hour, the speed of a casual stroll. They are not moving fast by any ordinary measure, a snail could nearly keep up. But because Andromeda is so far away, 2.5 million light-years distant, the tilt in their planes of simultaneity, the difference in what each of them would call the present moment in Andromeda, amounts to several days. The person walking toward Andromeda, if they could somehow see what was happening there right now according to their frame of reference, would see events that are, according to the other person's frame of reference, several days in the future. The person walking away from Andromeda would see events several days in the past. They are passing each other on a street, moving at walking speed, and they disagree by days about what is happening now in a galaxy 2.5 million light-years away. The disagreement arises because simultaneity depends on motion, and motion is relative. There is no preferred frame, no universal clock, no cosmic simultaneity that both walkers must agree on. Each of them has an equally valid notion of what is happening now in Andromeda, and those notions do not coincide. And if you ask which of them is right, the answer is that they both are. Relativity does not say that one of them has made a mistake. It says that the question, what is happening now in Andromeda, does not have a single answer. It has as many answers as there are observers, each moving at a different speed, each slicing through space-time along a different axis. Now return to the room, the daughter at her father's bedside. Imagine that this room is on Earth, and that the spacecraft is passing at 20% of the speed of light, and that an observer on the spacecraft looking back at Earth asks, what is happening in that room right now? The answer depends on the observer's motion. If the spacecraft is moving in one direction, the plane of simultaneity might pass through the room at the moment the daughter is holding her father's hand, the moment we started with. But if the spacecraft is moving in a different direction, or at a different speed, the plane of simultaneity might pass through the room an hour earlier, when the father was still speaking, or an hour later, after he has died and the daughter is sitting alone, weeping quietly in the lamplight. And if there are many spacecraft, moving in many directions at many speeds, then there are many planes of simultaneity, many different answers to the question of what is happening in that room right now, and all of them are equally valid. The implication is stark. If different observers, moving at different speeds, can disagree about which events in that room are present, and if there is no preferred observer, no cosmic frame of reference that picks out one plane of simultaneity as the true one, then there is no objective fact of the matter about which moment in that room is present. The conversation is present for one observer, the death is present for another, the solitude afterward is present for a third, and none of them is wrong. They are simply located differently in space-time, slicing through the same four-dimensional structure along different axes, obtaining different cross-sections, different snapshots of reality. And if that is true, then all of those moments, the conversation, the death, the solitude, must exist in some sense, must be located somewhere in the structure of space-time, not in the past or the future, but simply elsewhere, in regions of space-time that different observers assign to different categories depending on their motion. The breakfast when the daughter was 10, the morning her father burned the pancakes and they laughed. That moment is not gone. It is not erased from existence. It is located at a particular set of coordinates in space-time, and it is just as real as the moment of the father's death, just as real as the moment you are experiencing right now, listening to these words. The only difference is that your attention, your consciousness, your experience is not located there. It is located here, at a different set of coordinates, moving forward along your world line, constructing the present from the sensory inputs and memories and predictions that are available to you at this moment. This is the claim at the heart of the block universe, the claim that follows inexorably from the relativity of simultaneity. If there is no universal present, no cosmic now that all our observers must agree on, then the distinction between past, present and future cannot be a fundamental feature of reality. It must be something else, something perspectival, something that depends on where you are and how you are moving, like the distinction between here and there or left and right. The block universe says that all moments exist, tenselessly, laid out in a four-dimensional manifold, and that the experience of time passing, the feeling that the present is real and the past is gone, is a feature of consciousness, a feature of how you, as a localized observer, encounter the structure of space-time as you move along your world line. The argument was developed formally by philosophers and physicists in the 1960s and 70s. The Dutch philosopher C.W. Reitdijk published a version of it in 1966. The American philosopher Hilary Putnam, who had worked on the foundations of quantum mechanics and relativity, published a more detailed version in 1967. The argument is sometimes called the Reitdijk-Putnam argument, and it goes roughly like this. Suppose there is an event, call it E, that is in your future, something that has not happened yet according to your frame of reference. Because the event is in your future, you might be tempted to say that it is not real, that it does not exist, that it is merely possible. But now consider another observer, far away, moving at a different speed, such that their plane of simultaneity passes through event E. For this observer, event E is not in the future, it is present, happening right now according to their frame of reference. And if event E is present for them, then it must be real for them, because surely present events are real. But if event E is real for them, and if reality is not observer-dependent, then event E must be real, full stop. It must exist, not merely as a possibility, but as an actual part of space-time. And if that is true for every event in your future, then the future is real, just as real as the present, and the block universe is the correct picture. The argument is not universally accepted. Some philosophers argue that it conflates different senses of existence, that saying an event is present for one observer does not mean it is real in the same way that your present experience is real. Others argue that relativity only forbids a universal simultaneity for space-like separated events that cannot causally influence each other, and that this does not imply that the future is fixed or that all moments are equally real. The debate continues in philosophy journals and physics conferences, and there is no consensus. But the argument is powerful, and it is difficult to escape the conclusion that relativity, if taken seriously, pushes you toward the block universe. If simultaneity is relative, if there is no objective present, then it is hard to maintain that only the present is real, without also specifying whose present you mean, which observer's frame of reference picks out the real now. And if there is no preferred observer, no cosmic frame, then the idea of a privileged present collapses, and you are left with the block, the four-dimensional manifold, the static structure in which all moments coexist. Einstein himself seems to have believed something like this. In March of 1955, a few weeks after the death of his lifelong friend Michel Besso, and about a month before his own death, Einstein wrote a letter to Besso's family. It is a short letter, a condolence, and it contains one of the most quoted sentences Einstein ever wrote. For those of us who believe in physics, he wrote, the distinction between past, present and future is only a stubbornly persistent illusion. The sentence is often taken out of context, used to support the idea that Einstein believed time was unreal, that the flow of time was a fantasy. But the context is important. Einstein was grieving. He had lost his closest friend, someone he had known since his student days in Zurich, someone who had been there during the miraculous year of 1905, someone who had read and commented on his papers, including the paper on electrodynamics that introduced the relativity of simultaneity. And in the face of that loss, Einstein reached for physics, for the block universe, for the idea that Besso's life was not gone but simply located elsewhere in space-time, that the past was not destroyed but merely inaccessible, that the distinction between the moment of Besso's death and the moment Einstein was writing the letter was not a fundamental feature of reality, but only a feature of Einstein's perspective, his location along his own world line. Whether this is consoling or not is a personal question. For some, the block universe is a comfort, a way of holding on to what has been lost, a way of saying that nothing is ever truly gone. For others, it is cold, deterministic, a picture of reality in which the future is already written, in which there is no genuine becoming, no real change, only the static structure of space-time laid out once and for all. But consoling or not, the block universe is what relativity gives you, if you follow the mathematics to its conclusion, if you take seriously the idea that simultaneity is relative and that there is no universal now, a life, not a vanishing. And so we come back one last time to the question of how to live with this, how to hold the block universe in your mind without losing the texture of experience, the feeling that the present matters, that choices are real, that the future is open in a way that the past is not. The block universe does not take these things away. It reframes them, places them in a different context, but it does not erase them. You are still you, still localized in time, still experiencing the world from a particular vantage point, still constructing the present from memory and anticipation, still feeling the weight of the past and the uncertainty of the future. The block universe simply says that your experience, vivid and immediate as it is not the whole story. It is one thread in a larger structure, one world line among countless others, one path through the four-dimensional manifold. Your world line is fixed in the sense that it is a geometric object, a curve in space-time, something that can be described mathematically, something that has a beginning and an end and a shape. But you do not experience it all at once. You experience it sequentially, moment by moment, as your consciousness moves forward along the curve, encountering each event in turn, constructing the present from the sensory inputs and the memories and the predictions that are available to you at each point. The block universe does not say that your choices are not real. It says that your choices are part of the structure, that the decision you made yesterday, the decision you will make tomorrow are both located in space-time, both part of your world line, and that the fact that you have not yet experienced tomorrow's decision does not mean it is not real. This is a subtle point, and it is easy to misunderstand. The block universe is sometimes taken to imply determinism, the idea that the future is fixed, that everything that will happen has already been decided, that you are simply going through the motions, acting out a script that was written before you were born. But this is not quite right. The block universe says that the future is real, that it exists in space-time, but it does not say that the future is unchangeable. It says that your world line, the path you take through space-time, is what it is, and that you cannot step outside of it, cannot see it from the outside, cannot alter it from a God's eye view, because you are inside it, embedded in it, experiencing it from within. The choices you make are part of the world line, not imposed on it from the outside, and the fact that the world line is fixed does not mean your choices are not genuine. It means your choices are what fix the world line, what give it its shape, what determine the path you take through the manifold. This is not an easy idea to hold in your mind. It requires accepting a kind of perspective shift, a way of thinking about yourself not as a thing that exists at a single moment, a single point in time, but as a four-dimensional object, a world line that stretches from your birth to your death, a curve that contains every moment of your life, every decision, every experience, every breath. In the block universe, you are not a vanishing present that leaves a trail of non-existent past behind it. You are the entire trail, the whole curve, the complete structure. The breakfast when you were 10, the conversation you are having right now, the moment of your death, whenever and however it comes, are all part of the same four-dimensional object, all part of you, and none of them is more real than any other. They are simply located at different coordinates, different points along your world line, and if that is true, then loss is not what it seems. The father who dies, the moment that passes, the breakfast that feels like it has gone forever, these are not erased from existence. They are simply elsewhere in space-time, located at coordinates that your consciousness is no longer visiting, regions of the manifold that you have moved past that you will not experience again, but that are still there, still real, still part of the structure. The daughter sitting at her father's bedside, holding his hand in the lamplight, that moment is not destroyed when the moment ends. It is simply left behind, in the same way that the town you drove through an hour ago is left behind when you drive on. The town does not cease to exist when you leave it. It is still there, and if someone else drives through it, or if you turn around and drive back, it will be there, unchanged. The block universe says that time is like space, that the past is like the town you left behind, that the moment is still there even though you are not. This is the sense in which the block universe offers a kind of consolation, a way of thinking about loss that does not require believing that what is lost can be recovered, but that allows you to hold on to the idea that it is not gone, not erased, not nullified. The physicist Carlo Rovelli, in his book The Order of Time, writes about this with a kind of poetic resignation, saying that the past is not destroyed, only inaccessible, and that the grief we feel when a moment passes is not grief over its non-existence, but grief over the fact that we cannot return to it, that our world line moves in one direction only, that we are carried forward by the arrow of time, by the increase of entropy, by the one-way structure of memory and causation. The past is there, he says, but we are here, and the distance between here and there is not a distance we can cross. And yet, the block universe, for all its strangeness, for all the ways it contradicts our intuitive sense of time, is the picture that emerges most naturally from relativity. It is what you get when you take seriously the idea that simultaneity is relative, that there is no universal present, that the structure of space-time is a four-dimensional manifold and not a sequence of three-dimensional snapshots. Other interpretations are possible, other ways of reconciling relativity with experience, but they require additional assumptions, additional structure, additional metaphysics. The block universe requires only taking relativity at face value, following the mathematics wherever it leads, accepting that the universe is a static structure, and that time, as we experience it, is something that happens inside that structure, something that arises from the way consciousness encounters the manifold, something that is real for us but not fundamental to the universe itself. So what does it mean to be here, now, in this moment? If the moment is not the only moment that is real, what does it mean to listen to these words, to hold this thought in your mind, to feel the present slipping away into the past, if the past is not gone and the future is not yet to come, but both are simply elsewhere in space-time, as real as the present, as permanent as the geometry of the manifold? It means perhaps that attention is everything, that the block universe is a stage and consciousness is the spotlight, and the story of your life is not the story of the stage being built, but the story of the spotlight moving across it, illuminating one moment after another, bringing each one briefly into focus before moving on. The stage does not change. The world line is what it is. But the spotlight moves, and the movement is what you experience as time, as the passage of the present, as the transformation of the future into the past. And the spotlight is yours, and yours alone. No one else can experience your world line from your perspective, can construct your present, can feel the particular weight of your memories and anticipations. The block universe is shared, but the experience of it is private, local, irreducibly subjective. And so the ordinary moments, the ones that feel too small to matter, the breakfast with your father when you were 10, the morning he burned the pancakes and you laughed about it, these moments are not lost. They are part of the structure, part of your world line, part of the four-dimensional object that is you. They are located in space-time, at coordinates that you can specify if you know the date and the time and the place, and they are as real as the moment you are living right now, as real as the moment of your birth, as real as the moment of your death. The only difference is that your attention is not there. Your attention is here, now, at this set of coordinates, constructing the present from the sensory inputs that are arriving, from the memories that are available, from the predictions that are being generated. And the present you are constructing is not the present anyone else is constructing, because they are located at different coordinates, moving along different world lines, slicing through space-time along different axes. But the structure is the same for all of you, the static, silent, four-dimensional manifold, and the moments you have lived, the moments you are living, the moments you will live, are all part of it, all equally real, all equally permanent. The father and the daughter sitting at the breakfast table on a morning 30 years ago, laughing over burned pancakes. That moment is still there. It is still happening, in the sense that it is located at a particular set of coordinates in space-time, and if you could somehow step outside of time, could view the manifold from the outside, you would see it, frozen and eternal, a single frame in the four-dimensional structure. You cannot step outside. You are inside, embedded, moving forward along your world line, and the moment is behind you, inaccessible, separated from you by the arrow of time, by the one-way flow of entropy, by the structure of causation and memory. But it is not gone. It is there, in the same universe that contains your present moment, in the same manifold that contains everything that ever was and everything that ever will be. And that perhaps is enough. Not to recover it, not to return to it, but to know that it is there, that it is real, that it is part of the permanent structure of reality, and that nothing, not time, not death, not the relentless forward motion of your world line, can take it away.